lecture 8. Um, we are talking about how to analyze the properties of composites from basic properties. And uh, for that, we need to understand what are the fracture mechanisms controlling the properties of composites. How will they fail when they are put in different kinds of stress conditions? One thing to note is that the strength of a composite in tension is always more than it is in compression, especially if you have uni I mean continuous fibers. And that is because in tension the strong fibers take up the load. And even if they are slightly off axis, they can still take the load or take the majority of that load. But in compression, most of the time the fibers will tend to buckle because most of the time the fibers are like our hair. So if you compress that, it is going to start buckling. And that is also because the surrounding matrix is not very stiff or strong to support the shear stresses created, and there is a kind of a buckling or kinking that will start the fracture process. So what will happen is that this is the kind of fracture behavior that you will find. So if you have a tensile fracture, you will have these fibers, especially if the right kind of properties, right kind of fibers are taken, you will find that these fibers will pull out of the matrix on the opposite side, and they will have some amount of fiber pull out seen. But if you have compressive stresses applied on these composite materials, these fibers are going to buckle and they are going to break in the middle. So, in order to understand or to define these properties, there are two ways of looking at composite properties. The first one is called micromechanics, and the next one is called macromechanics. Macromechanics is more for structures and things like that. But micromechanics tells you what are the properties of one single lamina of the composite material based on the individual properties of the matrix and the fibers. And we already looked at that when we looked at the isostress and isostrain conditions. So most of the time what we do is we laminate these individual lamina, LAMINA, and we put them together, and this can then be either placed in a shape or form, or we might take these individual lamina and wind them around a tool or a mandrel. So macromechanics is the study of the stress strain behavior of composites if we know the effective properties of an equivalent homogeneous material. So in this case, we only look at the average stresses and strains, and we do not look at we do not evaluate the local fiber and matrix properties. And let's talk about that. And for that, we need to discuss this in terms of the stress strain relationships at an individual point within this material. And then we will discuss the concept of effective moduli for heterogeneous materials, for which the properties might vary from point to point. So this can be presented in a general form as sigma ij, where ij can be any point in the x and y plane, and it can be represented in terms of epsilon 11, epsilon 12, epsilon 13, etc. These are all the different strains in the individual directions. Now, so what you need to understand is that the stresses can be represented in terms of a matrix multiplied by the individual strains. And each component of stress has 9 strain components. And what you need to understand is that these relationships may be not linear at all or non-linear. Okay, so if you expand that, you have sigma ij, which have 9 components. Epsilon kl can be 9 components, and this global matrix has got 81 components. Okay, so this is a, if you don't consider anything, if you don't simplify the matter, this is how it is going to be turning out. So if you have an overall component, you have these three-dimensional state of stress. Now most of the time what will happen is that many of these stresses will turn out to be symmetric, so you can just um, not consider them, or some of these properties will be the same as in the other directions and so on. But assume that it is not the case. Okay, so you can represent this in matrix form. Sigma on one side, you have a matrix C with the different individual components on one side, and multiplied by a matrix consisting of the strain values, the 9 strain values. And this is the generalized Hooke's law for an anisotropic material. So if you have symmetry, for example, if you have symmetry of shear stresses and strains, that means tau 12 will be equal to tau 21, or in general tau ij equal to tau ji, or sigma ij equal to sigma ji, and epsilon ij equal to epsilon ji. So, and the same conditions for shear strains. And we can discuss material property symmetry for various properties. So if you have symmetry of shear stresses and shear strains, that means only 6 components are required for sigma or stress, and only 6 components are required for the strain epsilon. So this will give you a simplified version of this matrix. And when that is the case, we can, this is the tensor notation, and you can actually reduce that contracted notation. So sigma 11, because sigma 11 is the same as so on. So you can say that instead of sigma 11, you can say it is sigma 1, sigma 22 is equal to sigma 22, etc. So you have 6 states of stress for sigma. Same thing with epsilon. Okay. Now you can simplify this even further by saying that total change in original angle, the shear strain, is equal to gamma xy, and amount each edge will rotate is half of that, which will also be equal to epsilon. So if you do that, you can get a 6x6 matrix rather than an 81 matrix. So 36 values only are required. You can also invert that and represent epsilon in terms of sigma, and in this case you have another matrix Sij, which is the inverted matrix of C. Okay, so S is the called the compliance matrix, and C is called the the stiffness matrix. So S is the compliance matrix and C is the stiffness matrix. So these numbers, these matrices are called global stiffness matrix. And if you have learned about finite element modeling and things like that, these values and these matrices are extremely important for understanding that. Okay, so if you expand that, this is how it is going to be. So you can also reverse that and put sigma in terms of Cij times epsilon I. Okay. Now, this is only in case you are looking at these properties at a single point. In a composite, these properties will vary from point to point. So you have to use the concept of effective moduli of an equivalent homogeneous material. So same thing here, I mean, this is a little complicated. Don't go too much into detail about that. But what it does is you can come up with what is called an effective modulus C. So this is the stiffness matrix. So you can say that the effective stress is equal to the stiffness matrix times the effective strain, or it is actually an average stress and average strain. Okay, so it's an integrated over the entire volume. If you have symmetry, further symmetry, you can actually reduce the number of coefficients. So instead of 36, you only have 21. So if you do that, um, general anisotropic material, so you can, so what is strain energy density can be defined as, so in metals, what is that? That's equal to the toughness or the uh, compliance. And you can actually say that W is equal to 1/2 of sigma times epsilon. So for every individual point, you can get that energy, and if you integrate over the entire volume, you can get the energy density. So these things are, I mean, don't get too caught up in all this. These things will come up only when you are going to be talking about finite element modeling and things like that. So this is a way of representing all these all that the stresses and strains for individual points or over the entire volume. So for an anisotropic material, you can actually say that there are only 21 independent coefficients. So if you have symmetry, you can actually eliminate 1/2 of this matrix. Even with no material property symmetry. So, but if you have a what are called a specially orthotropic material, so where the fibers are all in one single direction, and 1, 2, 3 are the principal material coordinates, you can actually define the properties of this single lamina depending upon how the stresses are going to be applied. So you can actually represent epsilon 1 equal to the standard Hooke's law, sigma 1 over epsilon 1. Epsilon 2 is equal to, now if it is epsilon 2 in the second direction, you can actually write this in terms of Poisson's ratio, negative Poisson's ratio 1, 2 times epsilon 1, or you can say that epsilon 2 is equal to in terms of epsilon 1 or sigma 1 over epsilon E1 or modulus in the direction 1. So if you calculate all these values, you can actually represent the stress strain behavior of these materials. Most of the time these are going to be I mean, you're only going to be looking at the um, linear portion of the stress strain curve. Similarly, you can also do epsilon 3 equal to uh, Poisson's ratio, negative Poisson's ratio 1 3 times epsilon 1, and similarly you can do that. Okay, so the total compliance matrix and the stiffness matrix will actually simplify even further. Okay, so now if you know the Poisson's ratio in specific directions, you can actually calculate these uh, stiffness matrices and compliance matrices. Now, if you only have pure normal stress, there is no shear stress. So that means all shear strains are equal to 0. And if that is the case, you can actually simplify this further. So you can say that Poisson's ratio 1 2 is equal to tau 12 over G12, where you have G12 is the shear modulus and in the 1 2 plane, and many of these cases are going to turn out to become 0. So this becomes extremely simplified. So let me do this. So if you have an orthotropic material, you can actually represent this stiffness matrix or the compliance matrix in terms of the elastic modulus, E1, etc., and um, G, etc., and Poisson's ratio, etc. So if you know the stresses, the principal stresses, you can actually calculate the strains. Okay, so this becomes a very simplified way of representing these values. You have 12 coefficients, but only 9 are independent. Rest of them can be calculated from the other values. So, and if you have symmetry, you are also going to have Sij equal to Sji. That means you will end up with only 9 independent coefficients. So if you have an orthotropic material, it will need only 9 independent coefficients. The especially orthotropic case. Similarly, you have other cases where you have transversely isotropic and so on. So I won't go too much into detail. I'm not really sure that you are going to be that interested in this. But let's take the case of an isotropic material. If you have an isotropic material, the shear moduluses in the 3 different directions are equal to one single shear modulus. The elastic modulus becomes one single elastic modulus. You have one single Poisson's ratio, and the shear modulus and elastic modulus are coupled by the Poisson's ratio. So you only have 2 independent coefficients if you have an isotropic material. So if you calculate elastic modulus and Poisson's ratio, you can calculate the shear modulus of these materials. So if you want to represent this in matrix form, this is how it will be turn out. So if you have an isotropic material in 3-dimensional form, you can actually calculate in any given point x, y, or z, you can calculate the stress at that point in terms of the Poisson's ratio and the strains in the x, y, and z directions. Similarly, you can actually calculate the shear stresses along those same lines. So, and why do we want to talk about this? Is because we want to see where the material is. I mean, even though this is an isotropic material or a generally orthotropic material, how these properties are going to be at any given point x, y, and z. So you can actually take the a non-principal xyz axis and calculate those values based on that. Similarly, you only have 9 independent coefficients. So to make this especially for generally orthotropic material, you call this compliance matrix as S bar matrix. So this gives you the number of independent coefficients. So if it is a three-dimensional case, isotropic will have non-zero coefficients of 12, but only 2 independent coefficients. So you can kind of understand how these things are going to turn out. So from this. So again, you can represent this in different ways. So let me stop here for this section and start the next section, the remaining in the next section.